Hey, this is Mr. Janes, and in this video we're going to be talking about square roots, how to simplify them, and how to multiply with them. But before we get into that, we need to talk about what exactly a square root is. So, squaring, okay, raising a number to an exponent of 2, like this, and square roots, one of these things, also called radicals, are inverse operations. So that means that 3 squared is 3 times 3. Remember the exponent, the 2, we call that a square, tells us how many times we should multiply that 3. And since this is a 2, that's 3 times 3, or 2 sets of 3's, equals 9. And so the square root of 9, kind of inverse operation going backwards, is 3. Now 5 squared, since it's squared, it means it's multiplying by itself. It's 5 times 5, which is 25. So the square root of 25 would be 5. It's that inverse operation. A few quick vocabulary notes. This right here is called the radical symbol, and the number under it is called the radicand. This number right here is called the index. Now for a square root, technically we put a 2 here because we're undoing that x to the second, or that square. So a square root undoes it. Oftentimes, since we use square roots so much, we won't put that 2 there. But later in the year we'll talk about cube roots. If you've got x to the third, you can undo that with a cube root, or x to the fourth, the inverse operation would be a fourth root. But for now, we're just going to stick with square roots. And this little line above is called the vinculum. We'll probably never use that in class, but a fun little piece of trivia. Before we get much farther, we need to make sure that we know what the perfect squares are. This is going to be very important to us. So if you don't have these memorized by your times tables, make sure you do it quick. See if you can fill in what these are right here without me telling you. Pause the video right now and try and fill those in. Pause now. Alright, let's see if we remember them. 1 squared is 1. 2 squared is 4. 3 squared, remember 3 times 3, is 9. 4 squared, 4 times 4, is 16. 5 squared, or 5 times 5, is 25. 6 squared, 6 times 6, is 36. 7 squared, 7 times 7 is 49. 8 squared, or 8 times 8, is 64. 9 squared, or 9 times 9, is 81. 10 squared, or 10 times 10, is 100. 11 squared, or 11 times 11, would be 121. 12 squared, or 12 times 12, is 144. And 0 squared, well, 0 times 0 is just 0. So again, pause the video here and try to figure out these next 1, 2, 3, 4, 5 square roots. Pause the video now. Alright, here we go. So the square root of 16, well, 4 times 4 is 16, so the square root of 16 is 4. 81, well, 9 times 9 is 81, so going backwards, the square root of 81 is 9. The square root of 1 is 1, the square root of 49 is 7, and the square root of 144 is 12. Again, I'm thinking of going backwards, inverse operations. Now, what about numbers like the square root of 12 or the square root of 27? If we look back at our chart of perfect squares, 12 and 27 don't appear anywhere. If I ask what times what is 12, you don't get anything, right? What times itself is 12, we don't know. And it's actually going to end up being in decimal. So there's a few things we can do with that. The first thing we could do is to estimate by seeing what perfect squares our radicals fall between. So take 12 to start. Okay, what does 12 fall between? Well, 12 falls between, it looks like, 9 and 16. So the square root of 12 is going to be somewhere between the square root of 16 and the square root of 9. I'll put these greater than symbols here. So the square root of 12 is somewhere between those two. Well, the square root of 9 is 3. The square root of 16 is 4. So that means that the square root of 12, or radical 12, must be somewhere between 3 and 4. Could be 3.5, could be 3.6, 3.1, could be a whole bunch of decimals. We don't know, but we do know it's somewhere between 3 and 4. Pause the video here and try and estimate what the square root of 72 falls between. Alright, let's take a look. Well, the square root of 72, well, let's see. 72, it's greater than 64, but less than 81. So that means that it's somewhere between the square root of 64, greater than 72, greater than 81. Somewhere between those two. And the square root of 64 is 8, and the square root of 81, sorry, is going to be 9, so the square root of 72 must fall somewhere between 8 and 9. So we can say it's between 8 and 9. And our first one, remember, was somewhere between 3 and 4. Now, if you wanted to be even more precise, right, instead of saying between 3 and 4 or between 8 and 9, we could take out a calculator and get a decimal approximation for that number. So let's take out our calculators. Let's use my calculator. I'm going to press second, and there's the square root symbol right there, and then 12 under that square root, and enter, and I get 3.4641, etc. So I'm going to round to 3.46 to 2 decimal places. What was the next number there? It was 464, so that means I'll round just to 3.46. All right. Pause the video here and try and find the square root of 72 using a calculator. All right, let's take a look. So the square root of 72 is 8.4852, etc. So if I'm going to round to 2 decimal places, that means it's 8.48. I look at the next number, which is a 5. So that means I'm going to round to 8.49. I round that 8 up 1. Let's write that down. 8, I'm doing blue, 8.49. Perfect. Now the thing to remember is that the square root of 12 and the square root of 72 don't actually equal 3.46 and 8.49 because I rounded. So I'm going to draw this kind of squiggly equal sign, and this means approximately equal to. It means that it's not exactly 3.46 or 8.49, but we're just rounding or approximating here. Now that method is mostly preferred by scientists or engineers, because they often need to use these in calculations involving measurement and length, and so they're going to need some sort of decimal approximation to get as close as they can. But it's not preferred by mathematicians, because in math, whenever we round, we introduce error into our equation, right? We introduce some sort of error, and if you do a lot of math with rounding numbers, your answer can actually be quite far off from what you intended it to be. So in math, we don't typically use the calculator to get a decimal approximation. We're going to simplify the square root, and let me show you how we do that. To simplify a square root, we're going to first see if any of our perfect squares up here are factors of the number we're trying to simplify. So in this case, we've got the square root of 12. We ask ourselves, are any of these numbers up here factors of 12? Well, 4 is a factor of 12. Remember, a factor means that it divides 12. So 4 divides 12, or 4 goes into 12. So if I come down here, what I'm going to do is rewrite my square root a little differently. I'm going to write it as the square root of 4, okay, times, now what times 4 is 12? 3 times the square root of 3. I'm doing what's called making a factor tree. Now at this point, although I don't know what the square root of 12 is, I do know what the square root of 4 is. So I can rewrite that as 2. And as for the square root of 3, I'm not sure. So I'm going to leave that as the square root of 3. And so to simplify the square root of 12, I would create this factor tree, factoring out that 4, and leaving me with the square root of 3, and simplify to write 2 times the square root of 3, also pronounced 2 radical 3 or 2 root 3. Pause the video here and see if you can simplify the square root of 72. Let's take a look now. So square root of 72, what would divide, what perfect squares from up here again would divide 72? Well, 4 goes into 72, so I will break this down into the square root of 4 times the square root of 18. All right, great. And can I break 18 down any more? Well, I bet I can. What about 9? 9 divides 18. So the square root of 9, and what's left over? 9 times 2, the square root of 2. And I'll bring down that square root of 4 again. So the square root of 72 is the same as the square root of 4 times the square root of 9 times the square root of 2. And I know what the square root of 4 is. That's 2. I know what the square root of 9 is. That's 3. And the square root of 2, I'm just stuck with. So I'll write that again. And then 2 times 3 is 6. So the square root of 72 simplifies to 6 times the square root of 2, or 6 radical 2. Now, if you're having trouble seeing if 4 or 9 go into these numbers, if you're having trouble factoring, there is another method you can use. That requires a little more math, but it's a little bit easier. Let me show you what I mean. What you're going to do is draw a factor tree off of 12 using any numbers you can. It doesn't have to be 4, 9, 16, 24. It doesn't have to be perfect squares, just anything. So what goes into 12? Well, 6 times 2. Then I can break 6 down into 3 and 2. And then once you have that, you find pairs of numbers. So you got that pair of 2's. And if you've got a pair of numbers, that number can come outside the square root. So 2 can come outside the square root. Any numbers that are by themselves that do not have a pair have to stay inside the square root. So the 3 stays inside the square root. And so the square root of 12 simplifies to 2 radical 3. One way I like to remember it is by saying that if a number has a friend, it can come outside of this little square root house and play out here. If it has no friends, it must stay inside the square root. So how would that look for the square root of 72? Well, the square root of 72, let's see, factors into, I guess I could do 2 and 36. I could factor 36 into 2 and 18. I guess I can do 18 into 2 and 9, and then 9 into 3 and 3. And so it looks like I've got a pair of 2's, a pair of 3's, and a lonely 2 that has to stay inside the square root. So I'll rewrite this as 2 can come outside the square root, 3 could come outside the square root, and that 2 has to stay inside. So 2 times 3 is 6, radical 2. So this is just a second way to simplify your square roots if you're having trouble dividing out perfect squares like 4, 9, 16. This is another option. Alright, so let's simplify a few more radicals. I'm going to use this original method here to simplify these next 3 radicals. And I recommend you pause the video now and try them first. And if you like to use the other method right here, I'm not going to do that in the video, but I will show you the work once I'm done with using the regular method right here. So pause the video now and try these 3 radicals. Alright, let's take a look. The square root of 20, what perfect square is going to that? I know 4 does, so the square root of 4, and what's left over? 5. I know the square root of 4 is 2, and square root of 5, I can't simplify that anymore. Leave that as the square root of 5, 2 radical 5. How about 10? Well, wait a second. 4 doesn't divide 10. 9 doesn't divide 10. Do I have any other options here? No, nothing else divides 10. So what do? Well, if I broke this down using the second method, 10 breaks down into 2 and 5, but there's no pairs of numbers, so there's nothing I can take outside that square root, which means that the square root of 10 is as simplified as it gets. So that'll just be the square root of 10 all over. And now 2 times the square root of 1,125. Now the key to this one is to remember that we already have this 2 outside the square root. So as we do our calculations, we're going to bring that 2 down. So let's start. I bring the 2 down, and then what can I break 1,125 into? Well, it turns out I can break that down into the square root of 25 and the square root of 45. And remember, I'm looking for those perfect squares up my list, and I found that 25 goes into that. So then, can I break down 45 anymore? Well, I can't. 9 is a perfect square, and that goes into 45. So that'll be the square root of 9 and the square root of, what's left over? 5. 9 times 5 is 45. That's right. And I can bring down my 25 and my 2. And can I break down 5 anymore? No, 5 is a prime number. It has no other factors. So I'll just finish up here. I've got 2 times the square root of 25, which is 5, times the square root of 9, which is 3, and my leftover, which is the square root of 5. So 2 times 5 is 10, times 3 is 30, so this equals 30 square root of 5. If you prefer doing it out the alternate way that I showed you, here's how you could factor each of those 3 numbers. Now I've circled the pairs in green and the single numbers, the single factors in blue. Now I've written out the pairs of numbers outside the radicals in green, the numbers inside in blue, and don't forget, when you have a number already outside that radical, it needs to come down and join the rest of the factors already outside of that radical. And lastly, the fully simplified version of each of those 3 problems.